Here's lesson 2 of our curve sketching unit. In this lesson, we're going to find local max and min points by doing the first derivative test, and then also find absolute max and min points by testing endpoints of intervals and critical numbers. So let's start off with, this is kind of a bit of a review from the last lesson, where we're going to determine all the local extrema for this degree 3 function by finding critical numbers and then using the first derivative test to classify them. And it also asks us to state when the function is increasing and decreasing. So before we actually do the algebra that goes along with this, let me go over to Desmos and show you the graph just so you can see what we're going to be doing. So here's the graph of the function. We're trying to find the local max and min points. Notice there's a local max point right here at negative 386 and a local min point right here at 2, negative 39. How are we going to find those using the first derivative test? Well, notice at each of those points, the slope of the function, which can be represented with this tangent line, the slope of the function is 0 at that point and at that point. And the derivative tells us the slope of a function at any point, so if we look at the value of the derivative at those 2 points, notice they were 0. That tells us the slope of the original function was 0 there. So if we can figure out the derivative, set it to 0 and solve, we should get negative 3 and 2. And then how are we going to determine whether at those two x values there's a local max or min? We'll notice before this local max point, the original function is increasing. And I could tell that from the derivative because the value of the derivative tells us the slope of the function at any point. And notice that's positive. A positive value of the derivative tells us the slope of the original function is positive, which means the function must be increasing. And then after the x value of negative 3, notice that the function is decreasing, and I can tell that from the negative value of the derivative. So we'll test the value of the derivative before the critical number and after the critical number, and see that it changes from positive to negative, meaning the function switches from increasing to decreasing, which means there must be a local max at that point. And then over here, at this critical number, we know the slope is 0. Before that critical number, the slope is negative. I can tell that from the negative value of the first derivative. And after the critical number, the slope is positive. I can tell that from the value of the first derivative. So I know the original function goes from decreasing before the critical number to increasing after the critical number. So at the critical number, there must be a local min point. So let's go ahead and do all of that algebraically. So I said critical number a lot. We're going to have to find the critical numbers. And remember, a critical number is a number that makes the derivative of a function be either 0 or undefined. So let me find the derivative of this function to start with. F prime of x equals 6x squared plus 6x minus 36. Now I need to figure out how could this be 0 or undefined. Well, this is a degree 2 polynomial function. There's no way it could be undefined, but it could be 0. Let's set it to 0 and solve. I'm going to common factor a 6 from all 3 terms. I get x squared plus x minus 6. And now I have this quadratic in brackets that I could try and find numbers that have a product of negative 6 and a sum of 1. And those two numbers are 3 and negative 2. So I get 0 equals 6 times x plus 3 times x minus 2. Now that it's in factored form, it's easy to find the values of x that would make it be 0. If x plus 3 was equal to 0, the whole product would be 0. And x plus 3 would be 0 if x was negative 3. And if x minus 2 was 0, the whole product would be 0. And x minus 2 would be 0 if x was 2. So those two x values make the derivative be 0. So these are what we call critical numbers. So the critical numbers are negative 3 and 2. Now it may be useful for us here to also find the critical points. Well, I know the slope of the original function is 0 at an x value of negative 3 and 2. But where is the original function at an x value of negative 3 and 2? Let's actually find the y values that go with these x values. So let's evaluate what is f at negative 3 and f at 2. And I'll use Desmos to calculate those for me, but we're just plugging negative 3 and 2 into the original function. So at negative 3, the y value is 86. And at 2, the y value is negative 39, and I'll just have it label those 2 points for me here. Notice the y coordinates are 86 and negative 39. So our critical points are the points negative 3, 86, and 2, negative 39. At those 2 points on the original function, the slope of the tangent line is 0, which means they are potential local max or min points. So I'll label these critical points. Okay, now we can use the first derivative test to classify these critical points as either local max or min points. So I'll set up my first derivative test. And when you set up the first derivative test, you need a vertical line for negative infinity, each of the critical numbers, and positive infinity. So negative infinity, -3, 2, and infinity, making sure they're in ascending order. And what we're going to do is, within each interval that I've created, we are going to test a value in the first derivative, and then comment on what that tells us about the original function. So when we find the value of the first derivative, we're just going to look and see is it positive or negative, and that will tell us whether the original function is increasing or decreasing, which will then help us classify these critical points as either local max or min, or neither. So let me pick some values in the intervals. So between negative infinity and -3, let's pick an x value. I'll choose -4. Between -3 and 2, I'll choose 0. And between 2 and infinity, I'll choose 3. Now let's test these x values in the derivative. I'm going to use this factored form version of the derivative, but you could use the standard form version, doesn't matter. If I plug -4 into this factored form version, I would have 6 times -1 times -6. That's 36, which is positive. We just need to write the sign. The fact that the first derivative is positive tells us the original function has a positive slope at that point, which means the original function must be increasing at that point. And I'll short form increasing with INCR. So it must be going up to the right. At an x value of 0, if I plug that into the derivative, I would have 6 times 3 times -2. That's -36. So the first derivative is negative, which means the original function has a negative slope, which means it's decreasing at that point. And at an x value of 3, if I plug it in, I would have 6 times 6 times 1. That's 36, which is positive, which means the original function is increasing at that point. So I now know within each interval, I know whether the function is increasing or decreasing. Before an x value of -3, the function was increasing, and then after the x value of -3, the function was decreasing, which means at an x value of -3, that must be a local max point. So the point -386 is a local max. And then before the critical number of 2, the function was decreasing, and after the critical number of 2, the function was increasing. So at 2, the function must have a local min point. And if we look back at our graph, notice local max at -386, local min at 2, -39. The question also asks us to state intervals of increasing and decreasing, and since we have this table, we can do that. So when is the function increasing? The function is increasing when x is an element of numbers in either this interval or this interval. That's because those are the two intervals where the function is increasing. So I just need to define those two intervals, and I'm going to do it in bracket notation. So from -infinity to -3, or from 2 to infinity. So you can write it that way, or you could write it as an inequality, x less than -3 or x greater than 2. So I would take either way of writing it. The decreasing interval, well, there was only one interval where the function was decreasing. It was between -3 and 2, the function was decreasing. You can write it as the function is decreasing when x is an element of numbers between -3 and 2. And notice I'm using round brackets at each number. That indicates the number is not included. Because the function isn't increasing or decreasing at the critical numbers, it actually has a slope of 0 at those critical numbers. So you could write it this way, or you could just say x is between -3 and 2 using inequality signs. Part 2, we're going to talk about the difference between local extrema and absolute extrema. So in the previous example, we found local max or min values. And here's the definitions of local max and min values. The key thing here is, for it to be a local max or min, it has to be the highest or lowest y value within a given interval around that y value. For it to be an absolute max or min point, let's read the definition of that. A function f of x has an absolute max or min at point A if the y value at that point, so f at a, is the biggest or smallest value of f at x for all x in the domain. So it has to be the highest or lowest the function ever goes over its entire domain. So let's start by looking at a graph and finding local min and max points and absolute max or min points within this domain of this function. It says the function exists from x values between 0 and 10, including 0 and 10. Part A says identify the local max point. So find the points that are the highest within a given interval. So B is a local max because if I just look within this interval that I drew that box around, that point at point B is the highest in that interval. So B is a local max. D is also a local max. That point D is the highest in that interval I drew. So our local max points are B and D. Part B says identify the local minimum points. So we're looking for an interval where to the left and right of it, the y values are higher than at the point. So point C is the only point that meets that criteria. It's the lowest in that interval, where to the right of it and left of it, the function is higher than it. So point C is a local min point. Part C says, what do all the points identified in A and B have in common? So what do point B, C, and D have in common? Notice the slope of the original function at all three of those points is 0. And if you don't see that, well, the slope of the function can be represented with a tangent line. And if I were to draw a tangent line at all three of those points, the tangent would be horizontal. And we know the slope of a horizontal line is 0. So the value of the first derivative at all three of those points would be 0. So I'll say the slope of the function is 0 at all 3 points. And we saw that by seeing they all had a horizontal tangent line. Part D says identify the absolute max and min points on the interval. Local min and max points could be absolute max and min points if not only are they the smallest or highest the function goes on an interval, but it's also the highest or lowest the function goes over its entire domain. Well, let's look back. What's the highest the function goes over its entire domain between 0 and 10? It looks like point D is the highest the function ever goes. But what's the lowest the function ever goes? Point A seems to be the lowest the function ever goes. So the absolute max would be point D, and the absolute min would be point A. So the main takeaway I want you to have from this is that if we're trying to find an absolute max or min, we have to check the endpoints of a function and its critical points. The critical points, we find those by finding when is the derivative 0. And we saw that because we saw at each of those local max or min points, they had a horizontal tangent, which means the derivative would be 0 at each of them. So we could find those local max and min points. But that doesn't necessarily guarantee we have found any absolute max or min points. We would also have to test the endpoints, A and E. So the highest or lowest the function ever goes may be at an endpoint or may be at a critical point. So we'd have to test critical points and endpoints to find absolute max and min. And I put a reminder here, a critical number of a function is a value of A in the domain of the function where f prime of A is 0 or undefined. If A is a critical number, then point A f at A is a critical point. Let's look at the different scenarios for what critical numbers could be. And I went over this in the last lesson, so we'll go over this a little bit quicker this time. So if we have a value of x that makes the derivative be 0 or undefined, what could that tell us about the original function? Well, in scenario number 1, it could identify that there is a local min or max point there. So we notice at this point right here, the value of the derivative would be 0 because the slope of the original function at that point is 0. And I can tell that because it would have a horizontal tangent. Notice before that point, the function is decreasing, which means the derivative would be negative. And after that point, the function is increasing, which means the derivative will be positive. So if the function is decreasing before and increasing after, we have a local min point. So that's one scenario. Another scenario, like at this point right here, where the value of the derivative would be 0. I can see that because if I were to draw a tangent there, it would be horizontal once again. But in this scenario, that point is not a local max or min. Before that point, the function is increasing, and after that point, the function is increasing, which tells us the derivative is positive before and positive after. Since there's no change in sign in the derivative, we know that that is not a local max or min. So just because the derivative is 0 at a point doesn't necessarily mean it's a local max or min point. Scenario 3 is one where the derivative is undefined. And at this point right here, the derivative is undefined, because if I were to draw a tangent slope at that point, it would be perfectly vertical, and the slope of a vertical line is undefined. Now, at that point, there's a local min point. The function was decreasing before, increasing after, so yeah, it is a local min point right there, and we call that shape, we call that a cusp. So if the derivative doesn't exist at a value of x, there could be a local extrema there. Here's an example where the value of the derivative at a point, this point right here, would also not exist, right? The slope of the function at that point would be perfectly vertical. But in this scenario, the function's increasing before and increasing after. So the derivative is positive before, positive after, which means that point is not a local max or min. Just because the derivative doesn't exist at a point doesn't mean there's a local max or min there. There could be, like in the cusp scenario, or it could not be, like in this scenario. The fifth scenario is one we'll talk about a lot more when we look at rational functions later in the unit, but notice this function, the function 1 over x, doesn't exist at an x value of 0. Its derivative also wouldn't exist at an x value of 0. So in that scenario, 0 doesn't actually count as a critical number because it's not in the domain of the original function. In order for something to be a critical number, it has to be in the domain of the original function. Notice all 4 points I labeled there are on the function, which is why they're allowed to be critical points. Okay, and then at the bottom here is what we're going to do next. To determine the absolute extreme values of a function on an interval, find the critical numbers, then substitute the critical numbers and the x-coordinates of the endpoints of the interval into the function. So for example 2, find the absolute max and min of the function, this x cubed function, on the interval between -3 and 4, including -3 and 4. So let me just give you a visual representation of what we have and then explain to you what we're going to do. Okay, here's the x cubed function, but we want to limit the domain to be between -3 and 4. So there we go. We want to figure out what is the absolute max and min of this function in that domain. So what we need to remember is critical points, which would show up here and here, may be local max and min points, which may also be absolute max and min points. So we would have to find those points. But then we also have to test the endpoints of the interval. The endpoints of the interval may be the highest or lowest the function ever goes. So we'll have to test all 4 of these points I have labeled. The critical points, those are the ones that have a derivative value of 0, and the endpoints of the interval. So let's start by finding the critical numbers. Critical numbers are numbers that make the derivative be 0 or undefined. So let me find the derivative. It would be 3x squared minus 12. That's a continuous function. It can't be undefined, but it could be 0. So let's solve for when is this 0. We get x squared equals 4. X equals plus or minus root 4, which means plus or minus 2. So we have 2 critical numbers, positive 2 and negative 2. In order to find the absolute max and min of the function on this interval, I have to test those critical numbers and the endpoints of the interval into the function. So I'll make a note of that. Test critical numbers and endpoint of interval. And the function's called f at x, so we need to test f at -3, f at -2, f at 2, and f at 4. -2 and 2 are the critical numbers, and -3 and 4 are the endpoints of the interval. If we test all of those are all of the options for what could be an absolute max or min. After we test all of those in the function, we'll get the y values, and we can draw our conclusion about what the absolute max and min are. So we'll plug each of those into the original function. And I have Desmos already doing that for us here. Right, we have f at -3 is 6, f at -2 is 13, f at 2 is -19, and f at 4 is 13. So let's jot those down. So what is the absolute min value? What's the lowest the function ever goes? The lowest the function ever goes is at the point 2, -19, within that domain anyway. So this is our absolute min. So absolute min at 2, -19. And where's the absolute max? Absolute max at, well, notice the highest y value occurs twice. It occurs at an x value of -2 and at an x value of 4. They both have a y value of 13, and that's the highest the y value will ever be on that interval. So there are 2 absolute max points at -2, 13, and 4, 13. And hopefully you understand why the critical numbers and the endpoints are all we have to test. Because if we think about it, if the function was ever going to go higher than this endpoint here, it would have to go up above it and then turn back down. And anytime a function turns like that, that means it's going to have a local max point, which means at that point its slope is 0, so the value of the derivative would be 0. And we would have found that when we found the critical number up here. So all you have to do is test critical numbers and endpoints and check the y values and conclude what the absolute min and max are. Last example. It says the surface area of a cylinder container is to be 100 centimeters squared. Its volume is given by this function. Volume based on radius equals 50 times the radius minus pi times the radius cubed, where r is the radius of the cylinder in centimeters. Find the max volume of the cylinder if the radius cannot exceed 3 centimeters. So this formula gives us the volume based on whatever radius we want for a cylinder that has this specified surface area. Let's not worry about that too much. When we do more optimization problems near the end, you're going to have to come up with this volume formula, but for now I'm giving it to you. We want to know when is the volume at its max if the radius has to be between 0 and 3 centimeters. So let's write down, we have a restriction on our domain. Our domain, well, the radius has to be bigger than 0. We have to have a radius, but it says it can't exceed 3, so it has to be less than or equal to 3. So it's between 0 and 3. If I want to know what's the max volume, I would have to test the endpoints. So test 0, test 3 in the volume function. Well, I know if the radius is 0, the volume is going to be 0, so that's not going to be an absolute max. But I will have to test 3 and any critical numbers between 0 and 3. Because our function, and let me just show you what the function looks like. So here's the volume function, but we're restricting the domain to be only between 0 and 3. And if you notice, I have the points at the endpoints on there for us. The volume, if the radius is 0, is obviously 0, but the volume, if the radius is 3, is about 65. Maybe that's the absolute max the volume can be on the interval. The only way that wouldn't be the absolute max is if between those 2 points the function goes higher, which means you would then have to turn back down, creating a local max point that would have a derivative value of 0. So that would create a critical number. So we have to test and see, is there a critical number? And if we look at this, yeah, we're going to get a critical number right here at about 2.3. At that point right there, the function has a slope of 0, right? It has a horizontal tangent line. But let's do this algebraically. So let's find the critical numbers. Critical numbers are numbers that make the derivative, so let's find the derivative, be either 0 or undefined. So the derivative of the volume function would equal 50 minus 3 pi r squared. And now we'll solve this equation for 0. So 0 equals 50 minus 3 pi r squared. And now we just have to isolate r. So 3 pi r squared equals 50. R squared equals 50 over 3 pi. So r equals plus or minus, well, I don't actually care about the negative because we can't have a negative radius length. So I'll just do the positive square root of 50 over 3 pi. So let me evaluate that here. 50 divided by 3 pi. I need to square root this, so that means to exponent of half. And I get 2.3. And yep, that's the x value of that point right there. So it's about 2.3. So the radius is about 2.3 centimeters. So if we're finding absolute max on an interval, we just have to test critical numbers and endpoints of interval. And keep in mind this is a critical number. So let's do our test. Let's find the volume when the radius is 0. Well, that's obviously 0. The volume when the radius is 2.3. And the volume when the radius is 3. Now we've seen the graph, so we know that it's an absolute max at a radius of 2.3. But if we hadn't seen the graph, we'd have to evaluate each of these. So we'd want the volume at 0, at 2.3, and at 3. If we plugged into the equation, we'd get the y values that go with all 3 of these points labeled. We'll jot those down and see which y value is the highest. And these are approximate, 76.8 centimeters cubed and 65.2 centimeters cubed. So the absolute max on the interval would occur when the radius is 2.3. All right, that's it for this lesson. Make sure you try out the practice questions.